Hey everybody, I wanted to go through this problem for the marble launcher because if you are preparing for your upcoming test, then this is a good one to look at, make sure that you are feeling super strong about. It starts off with a good high school introduction through projectile motion, but really goes into good depth, and then this last problem, G, definitely takes it to a college level. So let's get started. This first problem tells us marble launcher that can launch a marble with a speed of 16 meters per second is set to an angle of phi equals 50 degrees above the positive x-axis. And it looks like that's what we see right there. I'm going to take care of this right now because we're definitely going to need it. But if this marble is being launched at 50 degrees at an angle of 16 meters per second, I want to break that into its x and y components, or ij components. Here, that part, our horizontal velocity, 16 cosine 50. It's going to be a horizontal velocity of 10.3 meters per second. And then our vertical velocity, 16.0 sine 50. That's a vertical velocity of 12.3 meters per second. That makes sense that the vertical velocity is bigger than the horizontal velocity. 50 degrees is above 45 degrees. We should have more y than we have x. To figure out all the information here about the marble as it goes to this maximum height, because the problem starts right here and ends right here, let's set up a table organizing our horizontal and vertical information. We'll put a little h for horizontal and a little v for vertical. And horizontally, our motion is constant. So all I care about in the horizontal direction is our displacement, our velocity, and our time. That horizontal x velocity will not change, but vertically we will see a change, because the force of gravity causes this marble to accelerate. So I'm going to care about these 5 variables. Horizontally, we already know our velocity is positive 10.3 meters per second. Setting my inertial frame at the origin is at the marble launcher, and then positive denotes to the right, positive denotes up in the y-axis. I don't, however, know the time, and I don't know the horizontal displacement. Vertically, I don't know the vertical displacement, but I do know the initial vertical velocity is 12.3 meters per second up. And I know the final vertical velocity is 0 meters per second, because we are talking about the maximum height. That shows up a few times here. A, this is the Earth, so I'm going to say negative 10 meters per second. If you were doing a lab, you would use 9.8, but in a problem, negative 10 is totally fine. It makes the calculations a little quicker, a little cleaner, a little easier. And then I do not know this delta t. So then vertically, I can say, okay, I'm trying to find maximum height, I'm trying to find delta t. Given VI, VF, and A, I can use this idea. VF squared minus VI squared equals 2A delta Y. And then that becomes 0 squared minus VI squared 2A delta Y, or delta Y equals negative VI squared over 2A. Well, let me plug in some numbers there. Negative 12.3 meters per second quantity squared over 2 times negative 10 meters per second. And then those negatives are going to cancel out, so this becomes 12.3 squared over 20. Gives me a delta y of 7.5, that's 6 meters in the positive direction. So I can go ahead and write that in as my answer to A. B, how much time does it take for the marble to reach this maximum height? Certainly there are calc things you could do here. You could say that the acceleration is negative 9.8, and if the integral of a dt is the velocity, then the velocity equals negative 9.8t plus 12.3. And you could plug in, hey, I'm doing it right now. 0 equals negative 9.8t plus 12.3. Bring that 9.8t equals 12.3. And I get t is equal to 1.26. That's the answer for B. You didn't have to do that with calculus. You could have just said A equals delta V over delta T. And essentially you can see that you are doing the same thing. It becomes A delta T equals V final minus V initial, and that's where that came from. Same. What is the horizontal displacement of the marble during this time? Well, if we go over here and the time is 1.26 seconds, this horizontal velocity is constant. So Vx equals delta x over delta t. Vx multiplied by delta t equals delta x, or 10.3 meters per second multiplied by 1.26 seconds equals delta x. Or a nice velocity of 13.0 meters, or a nice displacement. And you could say in the positive direction, I could say I to denote that that's the horizontal displacement. Totally good. What is the velocity of the marble at its highest point? So let me just note that that's the answer to C right there. Well, at the highest point, let me draw this out. Most common wrong answer for this is 0. In the beginning, this marble had a velocity of 16 meters per second at this angle of 50 degrees. And what that ends up being is a horizontal velocity that we've already seen of 10.3 meters per second and a vertical velocity of 12.3 meters per second. But up here at the highest point, Vy equals 0. That's what the highest point means. You're not going up, you're not going down. For a moment, you just stop vertically. But we still have all this horizontal velocity. No forces have caused the horizontal velocity to change. So the answer to D is 10.3 meters per second positive I. That's a horizontal velocity. And E, what is the acceleration of the marble at its highest point? Well, up there it is certainly still accelerating. That is 9.8 meters per second per second. You could say negative J. Because that is 9.8 meters per second towards Earth. That is still our acceleration. It is still just the force of gravity acting on this marble. So those are the answers to A, B, C, D, and E. A really good problem working through this projectile. But wait, there's more. Now, I want to be able to talk about graphs of this object. Well, real quick, its horizontal position as a function of time as it travels to its highest point. It just moves at a nice steady rate. Problem says sketch, so I don't need any variables, but just to show that it's a linear relationship of x versus t. Y versus t, in that same time frame, we should stop at our highest point because there's no longer any vertical velocity, and the slope goes to 0. Horizontally, we have a constant horizontal velocity, always at the same value. Vy versus t starts off positive, and then in that same time frame, oh no, I need a ruler. We're going to go with that. Assume that these are the same time frames. But if our v final is 0. And our ax versus t, no horizontal acceleration as this goes. And then our vertical acceleration is a constant negative number. And I actually know what that negative number is. It's negative 9.8 meters per second. So those are your graphs for a projectile. Good things to be able to do. G, now we take the marble launcher and fire it up this incline. G, I want to give myself some more space for, which is always a good idea in a problem. There's two ways to go about solving this problem. I'm going to do both, and I want you to be familiar with both and see both, so you can say, I like one or the other, but I could do both ways. Because there's aspects of this problem that both ways will help us in future problems. That some ways it'll be easier to rotate the axis, and other ways it'll be easier to do multiple equations and a system of equations and solve for the unknowns. So, as a reminder, it's being launched up this at plane on a 20-degree incline, still at that same initial condition. So all the things are still true about this marble launcher. If we look at its delta x, vx, and delta t, if we look at this horizontal information, and we look at delta y, v initial, v final, a delta t, the problem says the original conditions of the launcher still hold. So it's still at this 16 meters per second at 50 degrees. So I can just flip over and grab this 12.3. In the positive direction, set in my inertial frame. And then Vx is still positive 10.3 meters per second. The acceleration is still vertical, negative 9.8 meters per second, but we don't know the final velocity anymore. I don't know how fast vertically it was going at this point, because remember, this is just a vertical velocity. But what I do know is that this delta y right here, I can relate to this 20-degree angle and d. Delta y is d sine theta. And I'll just put that in here right now. On that same idea, this is d cosine theta. That's how far this goes horizontally. So I don't know time and I don't know time, but this is going to work out because I can set up a true equation about delta y. And I can say that delta y equals vi delta t plus 1/2 a delta t squared. And I can say that d sine theta equals, I will plug in numbers right now. I don't always plug in numbers right away, but I want to see what I know and what I don't. This is my vertical relationship. See that that's delta y, vit plus 1/2 a t squared. See that horizontally, d cosine theta, the x displacement equals Vx 10.3 meters per second multiplied by delta t. Math class, two equations, two unknowns. I can solve them for each other. It's actually a little easier for me to solve for t right now. So let me go ahead and do that. I'll say that d then equals 10.3 delta t over cosine 20 degrees. Reminder that we know that this theta is 20 degrees. So this becomes d sine 20 degrees over cosine 20 degrees equals no, I don't want to do that. I want to plug in this. I want to get rid of the d. Sine, see what's happening? I'm totally out of space right here, and this problem is becoming tricky. I need more space to work. Let me write down this thing again. D sine theta equals 12.3 t plus 1/2 negative 9.8 t squared. T just replacing delta t. And this feels so much better having space to work. D cosine theta equals 10.3 t, or d equals 10.3 t over cosine 20 degrees. Take this whole value and plug it in for that. 10.3 t multiplied by the sine of 20 degrees over the cosine of 20 degrees equals that original expression, 12.3 t plus, going to do a little mental math, 1/2 times negative 9.8, negative 4.9 t squared. Little algebra. 10.3 t sine of 20 divided by cosine of 20 is the tangent of 20. Tangent of 20 is 0.36 equals 12.3 minus 4.9 t squared, or one last simplification for now. 3.7 t equals 12.3 t minus 4.9 t squared, or 0 equals 8.6 t minus 4.9 t squared. And I want to solve for the time when this ball travels this far. When is that going to happen? When it has done that. In this case, I can actually factor out this t value. And this 0 time basically doesn't really help us. That it's nothing. Hey, just a second. What I care about is this value in here. I can solve for that. I'm just writing the same thing again. And say 4.9 t equals 8.6. T then equals 1.75 seconds. That ends up being the time where, like, that it takes for it to travel this distance d. What is that distance d? Well, I'll solve that back with my original equation for the x velocity. Vx equals delta x over delta t, or 10.3 meters per second equals d cosine 20, and what I now know is 1.75 seconds. 10.3 times 1.75 divided by cosine 20 gives us a d of 19.18, or sig figs 19.2 meters. From that distance d, you can solve for the velocity of the marble when it hits the incline. And really from just knowing that time. It's just simple plugging back in and knowing the x velocity and the y velocity at that point. And you should see that it's on its way down with its vertical velocity. I'll do it right now. V final then equals 12.3 plus negative 9.8 times 1.75. Means the final velocity is negative 4.85 meters per second in the vertical direction. Don't think that that's just the full velocity. That means we've got this 10.3 meters per second in the x, this 4.85 meters per second in the y, and our total speed is 11.4 meters per second at an angle of I'm actually going to find this angle and subtract it from 360. At an angle of 335 degrees. Which makes sense, that this marble should be on its way down. That's the only way it's going to collide with D. It couldn't collide with that point if it was still on its way up. The last thing I want to show you is a really novel approach to this one where you say, you know what? I'm actually going to define my inertial frame a little differently. I'm going to define my inertial frame, and I can actually, instead of saying the problem is like this, I'm going to tilt it and say that this is happening on what I'm going to call level ground. So that changes a few things about this. The marble is now being launched, still at 16 meters per second, but now at 30 degrees. The difference between the original incline and the original 50 degrees that this was being launched. And this marble travels this way. You can set your inertial frame like this. You can say, I am going to define this as the positive x direction, and this is the positive y direction. You are allowed to do that. You can tilt this problem on its head. The one thing that's different here is that this marble, because really this is the world right now. A person watching this would be standing right here. So the acceleration due to gravity is still downwards this way. But in our reference frame, x and y are what I'm going to want to split that acceleration into. So this 9.8 meters per second squared has been tilted 20 degrees back. So our vertical acceleration is now 9.2 meters per second squared, and we actually have an acceleration that's kind of pulling this back. That's 9.8 sine 20. Or I could say 3.35 meters per second squared. So this is how we can look at this one. I can say, all right, delta x, vi, vf, a, delta t. And I could say delta y, v initial, v final, a, delta t. Remember that this object is accelerating horizontally and vertically now. That's what we changed. Our reference frame. What is x? What is y? Well, delta x is d. It travels that way, plus d. V initial in the horizontal is 16 cosine 30, and that's 13.9 meters per second. I don't know the final velocity. The acceleration is negative 3.35 meters per second squared, and I don't know delta t. Delta y is 0. Marble comes back to the same height. V initial is 16 sine 30, or 8 meters per second. The final velocity is negative 8 meters per second, because this is symmetrical. So whatever our vertical velocity is here, opposite right there. And the acceleration is negative 9.2 meters per second squared. And delta t, I don't know. It is this question mark. But I have 4 knowns on this side. The only thing I don't know is the time. So saying A equals delta V over delta T, or delta T equals delta V over A. Delta V, we experience the change of negative 16 meters per second with an acceleration of negative 9.2 meters per second squared. Negative 16 divided by negative 9.2, we get a time of 1.74 seconds, which totally makes sense because that's the time we got before. 1.75, there's just rounding that messed that up. I can plug that time over here into 1.74 seconds, and then I can say, okay, well then delta x equals v initial times time plus 1/2 a delta t squared. And then, what am I looking for? That's the time, and delta x then is d equals 13.9 times 1.74, 24.2 meters plus 0.5 times negative 3.35 times 1.74 squared is negative 5.1, and 24.2 minus 5.1 is 19.1 meters is what d equals. The process for solving for the velocity is the same, but it's pretty neat that both ways gave us a solution to this problem. And I want you to be familiar with both. Can you set up a system of equations and solve through a problem, or can you tilt a problem on its head to make it a little easier to look at? Awesome. Print that problem out again, work through it on your own, solve it both ways for part G, and you'll be in good shape. Thank you.